Hello, and welcome to Lecture 2, where we're going to cover the second half of Chapter 1. These are sections 1.7 to 1.10 of Survey 11th edition. The topic of these sections is vectors. This is our introduction to vectors. Specifically, what we're going to do with vectors is define them, break them into components, add and subtract them. In fact, that's all we're going to do with vectors in this class. If you've seen vector multiplication before, that is not part of this class. All right, so let's get into our objective. To understand the vectors and their components, vector addition done algebraically and graphically, unit vector notation, and the multiplication of vectors with scalars, as well as the two ways to multiply vectors with each other. Key terms, all right? So first, let's define what a vector is and how it compares to something called a scalar. So, vectors and scalars are different types of physical quantities. What does that mean? Well, a scalar is just a number, a magnitude. For example, time is a scalar, so is mass. A vector, on the other hand, has magnitude and direction. For example, velocity is a vector. So is acceleration. Okay? Consider that a speed is a scalar and is the magnitude of velocity. Okay? Because speed doesn't have direction. It is just a number. And in fact, it is exactly the magnitude of velocity. It is the length of the vector. All right? So we denote vectors with an arrow. For example, v, and this is the vector notation, if we're typing it, we have it add a superscript of a little arrow on top of the letter, or graphically as an arrow itself, right? So this might be on, some sort of coordinate axis, okay? The length of this green vector, represented as an arrow, would be its magnitude, as direction can be defined relative to, for example, the x-axis as some angle theta, okay? But more on that in just a minute. Now we have a couple of rules for vectors. All right, these are the rules of vectors, and you can get into more of them in specific mathematics, but the ones that could come up are the cumulative law and the associative law. The cumulative law simply says that a plus b, right, that's an a vector, right, the arrow with a particular length, plus the b vector is the same as b plus a, just like with scalars. Okay, likewise, just like with scalars, a plus b plus c is the same as c plus b plus a. This is the associative law because it tells that we can group vectors. In other words, I could add b and c first and then add on a, or I could add b and a first and then add on c last. It doesn't matter, okay? Now, one way to talk about vectors, usually qualitatively and graphically, is to talk about tip-to-tail addition. This can be very helpful for giving us an idea about where a vector might point, a way to check our work, super applicable to things like relative velocity that we'll see in a later chapter. So what does it mean? What is tip-to-tail addition? As I said, it's a way to understand the addition of vectors. We'll get into the more kind of technical way to find the values of adding them. But first, let's look at it qualitatively. So if I wanted to add some vector A, this pink vector, plus an orange vector B, well, let's look at this, right? So A kind of points up and to the right, and B points straight down. So if I add those vectors together, what I do is I take the tip of A and I make sure that the tail of B touches it, hence the name, tip-to-tail addition. See that? The tail of the second vector, and again, it doesn't matter because as we know from the cumulative law, I could add B first, we get the same results, all right? And when I add them together, I get R. R is just the name I'm giving to the sum of the two vectors. And here I'm showing that clearly the commutative law works. Because in this case, I'm going to be adding b plus a, so then you see that I have the a vector is the pink one, kind of it's, the name is up above, but the a vector is coming second, so its tip is, or rather its tail on the pink vector is touching the tip of b right there. And if you think about it, then what you have, since this is b and this is a, you have a parallelogram. So adding any vectors will always form a parallelogram. In this case, it's a rectangle because one of the vectors happens to be straight down, but they could both be angled, in which case, you could have something like this, but the result is always a parallelogram. That's why sometimes the tip-to-tail addition is actually called the parallelogram rule. So moving on, let's talk about vector components. This is how we're going to start getting values and really talk about vectors in a quantitative way. All right? So we can think of every vector as a right triangle. All right, so why is that? Well, here we happen to form a right triangle by adding two vectors together, but we could actually think of either of these vectors as a right triangle relative to some coordinate axis. So let's consider. Vectors that compose another vector and which are parallel to coordinate axes. That is the definition of a vector component. Case in point, here is a vector A. It's not the same vector A. Obviously, it's a different angle and different length than the one up here. But here's some angled vector A. And notice, zoom in on this a bit, I've considered a component, the x component, and the y component. Those components are also vectors. They also have direction and magnitude, but they are defined to point exactly along the x and y axes, respectively. Thus, we've made a right triangle, okay? And theta is the angle of A relative to the x-axis, and phi is the angle of A relative to the y-axis, all right? And I could do that with any vector, all right? So if I take the magnitude of the x component vector of A, then I simply get a scalar, because anytime you take the magnitude of a vector, you get a scalar. And the length of that scalar is just A cosine theta. How do I know that? Well, I know that from SOH, CA, TOA, right? Because cosine is adjacent over hypotenuse. Well, adjacent is exactly the x component. The hypotenuse is the original vector. Well, then that's telling me then that cosine of theta is ax over a. If I cross multiply by a, I get that ax is just a cosine theta. That's where that definition comes from. That's why I can say the x component is a cosine theta. But I don't have to define it relative to the x-axis. I could define it relative to the y-axis instead, in which case a sub x, the x component, the magnitude of the x component of a, is a sine theta. All right, so you got to get used to the notation, used to the idea, magnitude, component, because we will be doing a lot of this right triangle trigonometry. All right, the magnitude of the horizontal component of A. That's what that is. Okay. All right, it looks like absolute value notation, but in this context, if you're doing it, taking the, using this notation around a vector, it means magnitude. All right, likewise, we could look at the magnitude of the y component of A, in which case it would be a sine theta and a cosine phi. Okay? All right, so key information there, and we'll get some examples of it in just a moment. All right, so likewise, since it's a right triangle, A, the hypotenuse, must be equal to the square root of the x component squared plus the y component squared. This is just the Pythagorean theorem. Furthermore, we can use the TOA part of SOH and then say that tangent theta is just the y component over the x component, which then allows us to solve for theta if we take tangent inverse of ay over ax. So if I happen to know the lengths of ay and ax, then I can find theta. Right? Sometimes you're given theta, sometimes you need to find it like this. And if you're interested in theta in terms of degrees, you got to make sure that your calculator is in degree mode, because this formula depends on whether you're in degree mode or radian mode. If you want your answer to be in radians, then you need to be in radian mode. Okay, just a word of warning. All right, so on to the concept of a resultant. Well, the term resultant is the reason I was using R, because we tend to refer to the sum of two vectors as the resultant. It is a name given to the sum of two or more vectors. Simply that. All right? Commonly expressed as R or sometimes uppercase R. All right? And always denoted as a vector with a little arrow above. So another bit of notation that you'll see in this class, in the textbook as well as in my notes, is I hat and j hat notation. I know it's kind of a silly name, but it's just a convenient way to talk about vectors. Helpful notation for vectors. The I vector is a unit vector that points along the x-axis. Hold up, what's a unit vector? Well, I'll tell you in just a moment. The j vector is a unit vector that points along the y-axis. So we could then consider our a vector from the definition above, where I defined what components are, and then consider these unit vectors. I'm calling this one j, that's that unit vector that points along y, and I'm calling this one I. They're short, I'll tell you why, but then what you could do is then you could express the vector a like this. And in doing so, notice I'm not talking about the magnitude of a, but I'm actually talking about the vector a, and I'm writing it as the sum of two vectors. So I'm essentially writing this in tip to tail notation in a sense. I'm writing this as a vector equation, not a scalar algebraic equation, but the vectors are the I hat and the j hat. And these are just the magnitudes, okay? Because I don't need to leave the whole magnitude notation. I can just drop it, as I showed up here, and just write it as a scalar, which implies that it's the magnitude. So it's the magnitude of the x component times I hat, the magnitude of the y component times j hat. Right? That's the same as just writing it like this, without the I hat, j hat. So why would you do it that way? Why would you even bother to write it this way? Well, because it's easy to follow, because the great thing about I hat and j hat is they're unit vectors, which means, drum roll please, it is just a vector of length 1, all right? Which is to say magnitude, because length and magnitude are synonyms in the context of vectors. All right, so that's the thing about I hat and j hat. They're vectors of length 1 that point exactly along whatever coordinate axes you're using, in this case x and y. And being length 1, if you multiply by the magnitude, it doesn't change the magnitude, right? So if I multiply by the magnitude of A, the x component, the magnitude of the x component of A, when multiplying by I hat, all I've done is made sure that the x component points exactly along the x-axis, right? Because, again, I has length 1, thus not affecting that value, okay? All right, so we'll do an example with that as well. So again, it's just an alternative way to express vectors. All right, let's quickly look through our key formulas. So this first formula, confirmed by tip-to-tail addition, is great. It tells a story, at least a graphical story. But check this out. This equation is useless for algebra. I bring that up because you can't say, like, solve for a sub y. I can't say, oh, well, a sub y is just a minus ax, and just kind of forget that they're vectors. This is not an algebraic expression. This is a vector expression. There is math that actually allows us to work with it. You can do actual like math on the page with this. You don't just have to draw arrows and maybe measure it by hand. But it is well beyond the level of this course. So for us, this is a dead end. We can't do anything with this equation. We have to split a into its components. We have to write x in I hat j hat notation, for example. We have to write y in I hat j hat notation. And only then can we actually solve for unknown values. Okay? All right? And this down here is just basically the same thing as I pointed out in the key terms. So what we're going to be doing most of the time is finding magnitudes. Here, this is just the magnitude of the horizontal component. We know that already. This is the magnitude of the vertical component, right? A cosine theta, a sine theta. This is the Pythagorean theorem. And here's the idea of finding the angle. Note that all of these equations are only true if theta is defined above the x-axis. Okay? So the fact that it's cosine theta and sine theta rather than sine theta and cosine theta on x and y respectively assumes that theta is measured relative to x, which it usually is, right? But not always. It makes sense to measure theta relative to x if I'm shooting a cannon above the ground and I talk about theta as being the launch angle of the cannonball. But if I'm talking about a pendulum swinging from the ceiling, I might want to measure my angle relative to the ceiling, okay? Or maybe relative to the pendulum when it's hanging straight down. Well, that wouldn't be theta, would it? That'd be what I called phi in the key terms. So you do want to pay attention to that. You always want to think, what are my angles? What's my picture? Draw the picture, make sure you understand the situation, which is really the golden rule of physics. You have to understand the situation and not just rush into the equations. Use the equations wisely. All right, so let's do some examples. There's only one type of problem here. Problems that mostly have multiple steps, but always involve treating vectors as the hypotenuse of a right triangle and using the Pythagorean theorem, or SOHCAHTOA, to find missing information about the triangle. Often two such triangles must be added together to make a larger triangle, the resultant. All right, so let's take a look at this first one. Two vectors exist on the xy plane. Vector A has a magnitude of 6 and points at an angle of 30 degrees above the x-axis. Meanwhile, vector B has a magnitude of 9 and points at an angle of 70 degrees above the x-axis. So both those vectors are fully defined. Knowing their length and their angle tells us their angle above a particular axis, in this case the x-axis in both cases, tells us everything that we need to know about that vector. Okay? Instead, I could have told you both their components, and that also would have been a fully defined vector. Right? So I want to kind of show you how, there's no unknowns about these vectors. But we're going to add them together, and we care about the resultant. What is the magnitude of the resultant of these two vectors? What angle does the resultant make with the negative y-axis? Oh, that's a totally different axis. Okay? So this is the picture we're going to refer to throughout both parts of this problem, part A and B. All right? So what's going on? Well, here's B, kind of drawn to scale, right? Because they were told that it was 9, so it was the longer of the two, and it's at a steeper angle. Here's A, the shorter of the two vectors, and at a less steep angle. Why is A way up here? Well, A is actually in two places. First of all, I drew A starting at the origin, just like I drew B, so they're kind of, both coming from a single origin. But here's the thing. I can move vectors. That's the whole reason tip-to-tail addition works. Vectors are and this was implied but not stated by me up to this point, vectors are defined entirely by their length and direction. Their location in space relative to the origin of some coordinate axis, relative to any point, is completely inconsequential. It doesn't matter. You could always move a vector and it's still the same vector. That's why I'm allowed to move A from here up to there. And in doing so, I can clearly see that tip-to-tail addition tells me that R is going to look something like this. Now that's nice to draw this. I like to draw this first because this tells me that the angle that R is going to make with the x-axis is going to be somewhere between 30 degrees and 70 degrees. Furthermore, R is going to be longer than either B or A. That's good to know, right? Kind of tells me what to expect, makes me confident that my answer makes sense when I solve for it. Okay, so this is what we're doing. R equals A plus B. But again, this equation is a dead end unless we split things into components. How do I do that? I take this expression, this vector expression, and I split it into two scalar equations. Scalar equations I can work with algebraically. It becomes something just like this, right? So A becomes A cosine 30 times I hat plus A sine 30 times J hat. These are just the X and Y components of A. See how that works? Okay. Meanwhile, I have a plus the X component of B and the Y component of B. All right? They're multiplied by I and J, so they're still vectors. Okay? And then I'm going to group them together. So everything that's attached to an I hat is a like term. Everything that's attached to a J hat is a like term. So we see then that the Y component of A and B get added together, and the X component of A and B get added together. And remember, these are just numbers, okay? I left the angles in here because I didn't want to have a bunch of different symbols representing the angles, so I just wrote them as 30 and 70. But I left A and B as variables, even though we know what they are. They're 6 and 9, right? Okay, so now let's actually plug in the numbers, the next step. Okay, so now we do that here. And then we can just solve for them, right? Because again, everything in the parentheses here is just a number. Everything in the parentheses here is a number as well. So then our final resultant vector in I hat, J hat notation is just 8 I hat times 11 J hat. That's it, okay? We have a fully defined vector. We've defined the vector. What were we asked for? We were asked for the magnitude of the results of these two vectors. So though I put a box around this, it's actually not exactly what we were asked for. We were asked for the magnitude. Is this the magnitude? No. This is actually the vector itself, right? This is, again, a fully defined vector. If I want to find the magnitude, what do? You're probably saying it to yourself, Pythagorean theorem, right? All I do is I just take the square root of 8 squared plus 11 squared, which gives me 14, all right? Now I cheated a bit here because I actually meant to rewrite this problem and give two significant figures to my magnitude on B, because technically there's only one significant figure here, so I should round this to 10, but I don't want to, so I'm going to cheat, and I added the significant figure. Because I intended to rewrite it anyway, I'm allowed to do that, you're not, all right? All right, but I won't cheat much, just this one problem. Okay, so moving on to part B. Okay, so it's easiest to find the angle between R and the y-axis and then add 180 degrees. What do I mean by that? Well, we have R right here, right? And then we can easily think of two components of R. We have Rx and, excuse me, Ry, and we have Rx. So I can think of those two components, think of then some angle here, I call that angle phi, and then, okay, that's great, then I have the angle of the R vector, the resultant vector, relative to the positive y-axis. But we were asked about the angle relative to the negative y-axis. So we were asked about theta, as shown here in the figure. Well, the only difference between the phi that I just talked about and theta, as shown in the figure, is 180 degrees, right? Or pi radians, for that matter. So just do an inverse tangent. So 180 plus inverse tangent of Ry over Rx, okay? Which numerically looks like this, 180 degrees plus inverse tangent of 11 over 8. All right, and then again, cheating and adding a significant figure, so it's not 200, it becomes 230. All right, 230 degrees. And again, I'm totally okay with you giving me answers anytime, in either radians or degrees, unless specified. In this case, it wasn't. I just said one angle, right? I think degrees are maybe easier to think about quickly. There are some times we have to use radians when we're doing oscillations, but for now, either one. Okay, let's do another example. All right, this is going to be our last example to wrap up this lecture. Example 2. I've decided to include this one as well, just to get some more practice of I hat, j hat notation. All right, so what vector must be added to A to get R? Okay, include a sketch to support your mathematical solution. All right, so the idea is that R equals A plus B. The resultant is A plus B. All right, but we weren't asked for R this time, unlike the previous one. And furthermore, we were given kind of more direct information, so we can kind of maybe do a faster calculation here. But first of all, you realize we have to solve for B. Well, B then is just going to be R minus A, right? We're totally allowed to do that. You know, we're just moving vectors around. Okay? Now let's rewrite them in I hat, j hat notation. Okay? So we know R is this right here. Okay? I don't have to put it in parentheses because it's the leading term. And then I'm going to subtract A. There I do want to put in parentheses to remember that my negatives are going to distribute onto both the I hat term here and the j hat term. So it'll look like this. Okay? Or I skip a step. So I distribute the negative. So it becomes negative 12 I hat minus 2 j hat. And then, just like with the previous problem, I group everything together. So I group all the like terms, all the I hat terms together, and all the j hat terms together. Right? So notice, right? Negative 6, negative 12. All right? Positive 14, and negative 2, because that's distributed negative. All right. Clean it up a bit, and there we go. In this case, look what it asked for. It asked for the vector itself. So this would be the final answer. We weren't asked for the magnitude. Okay? This is vector B. What does that look like? Because it said, you know, include a sketch to support a solution. Okay? So here's the coordinate axis. All right? Here's our R. We know that it's negative 6, positive 14. Right? So it's taller than it is long. Right? So that's why I have it in a more vertical direction. Okay? And then here is A. Okay? A is positive 12 in the I hat and positive 2 in the j hat. So it's much longer in the x and goes up a little bit in the y. We could also think about these in terms of quadrants, right? A is in the first quadrant, R is in the second quadrant. All right? And then we need to add something to A to get R, right? That's B, of course. And there it is. There's B. You know, and we could just as easily put B over here, right? This is also B because its location doesn't matter, right? And there it is. And we see that, sure enough, B is negative x directed and positive j directed. Well, positive y directed, right? Because remember, I is associative x, j is associative y. You get used to it. All right. So there's your picture. We got a nice triangle here. Is this a right triangle? No, this is not a right triangle. Adding vectors together doesn't have to make a right triangle. We can split any of these vectors into a right triangle relative to the coordinate axes, x and y, right? But this is not a right triangle. Good to remember. All right, so those are our two examples. You have some more you can work on and post the solutions if you're so inclined. Thank you so much for watching the second lecture video.